we care about state preparation? We would like to solve some real world problems with classical computers. And the typical process goes like this. We start with our classical database. It says financial data, or maybe it's an algebra mathematical function. We define our problem, and then we go with our problem into the content block, where we invest into encode our data, and then perform the optimization, hoping that it will give us speed up over the classical. If we do that, if we do all of that on hardware. The only problem is that even if you come up with a clever optimization method, if you cannot encode your data fast, you run out of coherent time on a multi-classical computer even before you start solving the problem. That's why it's an important subroutine. And this is the part we focus on within the Neuron or Quantum Response Memory Consortium, two institutions around Germany. In this talk, I'm going to focus on aptitude encoding, which is like the most general encoding, where you take your data, say it's real or complex number, and you write the data as the amplitude over quantum space. So, of course, you have an exponential storage capacity. You can store a lot of data, but in order to prepare such a state, you need an exponentially deep circuit in general. You can do with plastic sources if the state is structured, and the specific structure we want to exploit is the matrix product state structure. So this is how our pipeline looks like. We start with a set of probability aptitudes. We want to go to an MPS solution. Here, hiding out the one dimension. And we want to arrive at a final circuit that will approximately realize the state with a good fidelity. The first thing we want to do is compression. So typically, you would just do singular variable composition in a vector sequentially. You need to read out or store memory the whole state vector, and you will get the MPS format. What if your MPS composed of, let's say, 100 sites? How can you do SVD on such a large input data set? Well, if the rank of the MPS is limited, you know that you don't need to query your data set for all possible data points. Instead, you can query only n chi² for them and compare the MPS with the so-called tensor cross interpolation algorithm. And you have certain guarantees concerning the error. Now, you went from vector of 2 to the n number into a physical system of qubits. But you can never be sure that you accidentally didn't entangle, let's say, the first qubit and the last qubit at a very large distance. It will be a very inefficient representation in terms of MPS. So you can look at the relation between qubits or entanglement between them, and maybe you can reorder these qubits so that qubits which talk to each other more strongly are also close together in MPS. This is an algorithm I'm going to focus on in the second part of the presentation. And now you have the MPS. So you want to map it into a quantum circuit. So the main thing to do would be to assume a certain variational ansatz of an MPS, the whole circuit, try to optimize it. But if the system size is large enough, you typically go into problems of barren plateaus, vanishing grids, etc. It's a hard optimization task. But not if you start from a good enough initialization. So this is the thing you can do. And we're using two methods. And the first method is called sequential. We call it sequential matrix product disentangle. So basically, step layer by layer, you approximate your MPS with Scalable. Another method is something we call record disentangle, which was recently developed by another group. This was also 6 years ago. So here you end up with a virtual circuit, and each of these small unitaries is optimized independently by solving a strictly local optimization problem. You can introduce certain enhancements to these methods to minimize the number of gates and the circuit depth as much as possible. And after when you have these heuristically initialized circuits, you can fine-tune them with variational optimization. And one of such methods is called the Vidal optimization, which is nicely suited for optimizing circuits, keeping the MPS format all throughout the simulation. So you switch gate by gate, and then we optimize the gate to maximize fidelity, and everything is kept in the MPS format. An alternative way of optimizing the circuit would be reminder optimization, where you take all of the unitaries into account at the same time, and you do a gradient descent optimizing fidelity. But since you want to stay on the unitary manifold, you need to take the curvature of the manifold constraint. The problem with this one is that you cannot keep everything in MPS format. So in the limit of these circuits, many tensors, it becomes exponentially hard to. So you can combine all of these methods together and arrive at the final circuit. So let me focus. So in this presentation, I cannot focus on everything, but I will just focus on the two heuristic initialization methods. So SMPD. So how do you construct a layer of SMPD? Now you start with the MPF, and you analyze the MPF and truncate all the bonds to one dimension by one. And you choose the center of orthogonality and keep this about at the bond. And now you perform a trick. Since you have isometry, you can add legs, which are dummy legs for tensor without changing anything. And as you now, and you can now reinterpret this kind of tensor network as a quantum circuit, where you want to preserve the input and output of each tensor. And since you started with isometries, here you end up with unit. Here you just add columns to isometry to make it a unitary column. So you have this pi equal to nothing. And now you take your state and you apply the inverse of your circuit, nothing, to the state to get this entangled state. So you have one layer of unitaries, and now you can proceed in a loop and a one loop. So that's one. Nice thing about it is that you can do certain enhancements. So for example, since many unitaries that will be there in the circuit have one fixed leg, you can exploit this isometry structure, and instead of requiring 3 signals unitary, you can realize it with only 2. 3 signals will be necessary for example. Next, when you're disentangling, so you will be the state you disentangle. After some point, maybe you disentangle enough, well enough that you no longer need to disentangle. So you can just not apply it. So you can measure that it's the entanglement and it's not enough. You can stop doing the disentangling locally. And finally, depending on the gauge which you choose, or the center of orthogonality which you choose for your MPS, you can end up with circuits of different depths. Probably the best is to have a center of orthogonality in the center of the circuit. Okay. Now let's get to the brick run. So here the idea is from mathematics paper. So you transform your MPS into the data stage. So here the Schmidt value stay on the bond. And when you apply an operator around the bond, subtract it, and do it again, you can see that the only tensors you affect are the bond tensors, lambda, one tensor lambda, around which you apply unitary, and the gamma side tensor. So in a sense, when you apply this unitary, you only affect entanglement at a single bond. Meaning that if you want to, another task is to optimize the unitary variation rate so that you decrease the entanglement. So you can see that you can do that in parallel. Or odd bond, then even bonds, even bonds, and so on, until you reach a state of zero, to which you have to rotate it. In fact, the circuit you get a state of zero. Okay. So let me talk about benchmarking. So before I start, we need to mention something called quantity representation. So it's a way of encoding a function f of x on an interval, which can always be rescaled from 0 to 1. So we have a function f interval. And quantity representation tells you how to map the state of the qubit to floating point position on the interval. With the first qubit, we say whether we are in the left or the right half. And choosing the state of the next qubit, we say whether we are in the left, right half of the previous, and so on and so forth. So you see that you could get an exponentially good spatial resolution. And when you want to say what is, for example, the amplitude, probability amplitude for a given bit stream, we have a qubits, you just go along the path. Bigger, and the value of the function here will correspond to that. So we test our methods with two examples. The first one is the Gaussian distribution, 30 qubits, starting with 13. And here below you can see the entanglement entropy at each bond as a function of the bond. So literally after the first bond, there is no more information gain because well, the function is smooth and it doesn't matter if you put but you just don't get. So this one is, and then we have the Levy distribution, which is a Habitative function. It's much more complex, and it's relevant to the confinement because we make multiple samples. Here we deal with it. So this one is a bit harder. And it's encoded on an interval from 0 to 5. Then we have a in the factor, 29 qubits, to generate the function. And so we chose it not only because it looks cool, but it's also somewhere on the border we compare some regularity. And then we have data set of financial stock prices, S&P 500, 19 qubits, arranged next to each other. So this one is the most complicated. So we took combinations of our methods. We found that, well, all of these data sets could be prepared with feasible number of gates, and also that the methods converging in terms of the convention. We also found that these heuristic methods are not enough if you want to achieve those finalities. You need to also include the range. Whether you should choose SNPD or BNPD depends if you prefer less gates or lower depths. So that's the main. Here are just the numbers of denotes required for certain. So now back to the qubit reordering. Let's say you have 5 qubits, 4 qubits, and some of them talk to each other more than the other. There. So you can measure that with quantum mutual information between qubits, and you draw a quick line with the quantum mutual information. Right? You want to assign them in the positions of the qubits. So perhaps you would like to put qubit 1, qubit 4 close together in position x and y, so that the representation is. It turns out that this problem is fully analogous to a problem optimization, where you have certain number of facilities which have certain flow computing that. So let's say one operator is something that another partner will consider, and you want to assign them into CPU on the map. So this is now for the assignment problem. You want to minimize the total cost of the order. So you basically minimize the cost function, and you're trying to find an optimal permutation. And we really found an example where this reordering helped. So this is an example of a function which has two very different length scales. One is order of 1, so it's a big sign, and another is part of the regular sign on top of this. If you compute the quantum mutual information, you see that qubit 1 talks to qubit 12, and the algorithm for the assignment problem solver just brings those qubits together. So later, when you do take preparation, you just drop by what the hook magnitude. So that this makes. Okay, so with that, I'd like to thank you.
You mentioned that variational optimization methods are necessary, something like this. But I think we haven't really compared against any other methods, right? Like optimization methods, for example. You tried like integer programming, set solvers, or nonlinear optimization. Like there are many methods, not only
Yeah, of course. So there are even like exact methods where you map your MPS tensors exactly to a circuit, but then you end up with deep circuits. So when you decompose these unitaries into elementary gates.
If this is like a global optimizer, then you will come up with the shortest possible circuit, right?
Yeah, but here you're living in a very high dimensional space. So let's say you have 50 qubits, 2 to the 50. So when you start from a random initial point, the signal that will guide you towards the solution will be 2 to minus 50 because of this vanishing gradients problem.
Like in one of the co-authors of Qiskit, and I don't think that variational methods have been successful in any of the compiling tasks of Qiskit.
Well, what do you mean that they were not successful?
Well, like empirically, they're not very successful, right? Like there is this like
Yeah, but
readily available sort of benchmark where you can test against like dozens of other methods, and it's used by billions of sort of compiles every year, and you could sort of test freely against that.
yeah, of course there are many, but there are not so many, for example, which will stay within the MPS manifold, right? Because you may want to do a full scale simulation. So this FMBVDAR, for example, it scales very well because the complexity is just a contraction of two MPSs. So in that regard, it differs from methods you would normally encounter in case qubits. And another thing we employ here is starting from a good initialization, meaning that we can use simpler methods for variational optimization, let's say, because we are already close to the solution. But of course, the space of possible optimization methods is enormous. So we could choose whatever, given different circumstances, such as system size is limited to exact calculation, or I don't know, use of parallelization, etc.
Thanks for the question. Are there any so we make it complex. So you touch on the subject here.
Yeah, so there was, for example, a paper where, if you want, where they prepared a Gaussian centered around 0, so both sides, and it was more efficient to prepare one half of the Gaussian and then make a control gate with the second half rather than prepare the whole Gaussian at the same time. So you can find tricks like that. Yeah.